Imagine a planet roughly the size of Jupiter circling so close to its star that if that star were still its original size, this planet could never have survived. This isn't science fiction. This is a real confirmed discovery, studied in detail by the James Webb Space Telescope, a planet that, according to the standard rules of physics, simply shouldn't be there. In this video, we're going to talk about what James Webb Space Telescope actually discovered, why scientists are calling it impossible, and what this discovery can tell us about the future of our own solar system. If you enjoy real, verified space discoveries, make sure to watch this video till the end. This discovery was published in the journal Nature in July 2026, and it immediately became a talking point across the space community worldwide, not just because it's a genuinely puzzling object, but because it has a direct connection to the very distant future of our own solar system. Whenever a discovery shows us what our own fate might look like, it stops being just academic curiosity. It becomes a deeply personal, almost philosophical question. To understand this story, we first need to understand what happens to a star in the final phase of its life. Our Sun, and many other stars like it, become a red giant near the end of their lives, meaning they expand to more than 100 times their original size. When our Sun reaches this phase, roughly 5 billion years from now, it will expand so much that it will completely swallow Mercury and Venus, and Earth itself may also be destroyed in the process. At that time, any planet too close to the Sun will similarly be consumed inside this expanding star. After the red giant phase, the star sheds its outer layers entirely, leaving behind only a small, compressed, hot ember known as a white dwarf. A white dwarf is much smaller than its original star, sometimes even as small as Earth, but its density is so extreme that a single teaspoon of its material could weigh as much as several tons. According to standard theory, any planet orbiting too close to its star should be destroyed during the red giant phase, because during that phase, the star expands so dramatically that it completely engulfs the planet. White dwarf stars are actually quite common throughout the Milky Way. Scientists estimate that nearly 97% of stars in our galaxy, including our own Sun, will eventually become white dwarfs. Because of this, searching for planets around white dwarf systems isn't just a rare curiosity. It's a way of understanding the long-term future of a huge portion of our galaxy. If we can figure out how planets survive around these dead stars, we can indirectly learn what the eventual fate of countless planetary systems across our galaxy might be. That 97% figure itself highlights just how common and how normal the white dwarf phase actually is in a star's life. Only the largest, most massive stars end their lives through supernovas or collapse into black holes. Nearly everything else, whether medium-sized stars like our Sun or smaller red dwarfs, eventually becomes a white dwarf. That's why discoveries like WD 1856b aren't just isolated case studies. They give us a glimpse of the fate awaiting most planetary systems in our galaxy, including our own. That's exactly why when astronomers first discovered a planet called WD 1856b, they simply couldn't believe it. This planet is about the size of Jupiter, and it completes a full orbit around a white dwarf star in just 34 hours, meaning it's only about 2 million miles from its star. To put that in perspective, Earth is roughly 93 million miles from the Sun. That means WD 1856b is 50 times closer to its star than Earth is to the Sun. If this planet had always been this close, it would certainly have been destroyed during the red giant phase. And yet, it's alive, maintaining a stable orbit right where it is. This planet was first discovered by NASA's TESS mission, the Transiting Exoplanet Survey satellite, along with the now-retired Spitzer Space Telescope. The system is located roughly 80 light-years from Earth. When scientists began studying the planet's details, they found that it's 7 times larger than its own star, because a white dwarf itself is roughly Earth-sized, while WD 1856b is Jupiter-sized. It's strange even to think about, a planet 7 times larger than its sun, still orbiting that very star. TESS's job is essentially to continuously monitor the brightness of thousands of stars, watching for any planet that might be passing in front of them. When a periodic dip appeared in the WD 1856 star's brightness, meaning its light dimmed slightly every 34 hours, scientists immediately recognized it as a transit signal. But when they calculated just how large that dip was, they simply couldn't believe it. A dip that large was only possible if a planet several times larger than its own white dwarf star was passing in front of it. This was itself the first and biggest surprise of this entire discovery. This discovery was so puzzling that scientists turned to the James Webb Space Telescope to solve it, the most powerful and sensitive space telescope we currently have. Ryan McDonald of the University of St. Andrews, the lead author of this research, explained that the planet is 7 times larger than its star, a comparison that itself highlights just how unusual this system really is. The James Webb Space Telescope studied this planet during a transit, meaning while the planet passes in front of its star, blocking part of its light. Using this method, scientists measured WD 1856b's mass, which turned out to be somewhere between 4 and 11 times the mass of Jupiter. Alongside that, Webb also detected molecules in the planet's atmosphere, a historic achievement in itself, since this was the first time the atmosphere of any planet orbiting a white dwarf had been directly detected. But the most surprising part came next, when Webb measured the planet's temperature. During the transit, Webb detected infrared light being emitted by the planet itself, and the data showed that WD 1856b's temperature is roughly 260 degrees Fahrenheit or 126 degrees Celsius. That temperature was so high that if the planet's only heat source were the faint glow of its white dwarf star, it simply shouldn't have been anywhere near this warm. This extra warmth turned out to be the key clue that helped scientists unravel the mystery of this planet's orbit. It's important to understand that white dwarf stars emit dramatically less light compared to their original star. While a normal star like the Sun continuously gives its planet significant heat and light, a white dwarf only radiates a faint glow from its residual heat, much like a fire that is already burned out, with only its embers slowly cooling. So scientists calculated that if WD 1856b were only being warmed by this faint starlight, its temperature should have been very low, likely close to freezing, but the actual measurement showed the planet was significantly warmer than expected, which was the strongest evidence that something else was heating this planet, something tied to its history, not its current position. Christopher O'Connor of Northwestern University, who worked on this research, explained that the biggest question was how WD 1856b ended up where it is today. According to him, there are 2 possible theories. The first theory is that when the star was in the final phase of its life, it swallowed this planet, but the planet somehow survived from inside the dying star. The second theory is that the planet arrived at its current location through migration, meaning the gravity of other objects in the system gradually pulled its orbit inward. This white dwarf is actually part of a triple star system, meaning there are 2 companion stars alongside it, whose gravity may have influenced WD 1856b's orbit. Scientists tracked the planet's cooling history, meaning they calculated when it got hot and how much it should have cooled since then, and determined that this heating event likely occurred somewhere between 3 and 5.5 billion years after the star became a white dwarf. This means the planet was originally in a wide orbit, where it was completely safe from the red giant phase, and only afterward gradually migrated closer to its star. O'Connor explained that as the planet moved inward, its interactions with the white dwarf's strong gravity would have heated it up significantly, and it has been slowly cooling ever since. That's why, even today, this planet's temperature is higher than expected. It's the leftover residual warmth from that ancient heating event. Now, let's talk about what might be the most exciting part of this whole story. Webb Space Telescope also detected chemical fingerprints in the planet's atmosphere. Victoria Boehm of Cornell University, part of this research team, explained that they saw signatures of small cloud particles and hydrocarbons, most likely methane. This was the first time an atmosphere had ever been observed on a planet transiting a dead star, a white dwarf. Finding methane and hydrocarbons is itself a significant result, because it shows that WD 1856b's atmosphere still retains a substantial part of its original chemical composition, despite the fact that this planet must have been extremely hot at some point in its history when it migrated. If this planet had been completely cooked during that migration, its atmospheric molecules would have broken down entirely. But the continued presence of complex molecules like methane shows that this planet, despite its turbulent history, has managed to preserve much of its chemical identity. This discovery was so exciting that the research team immediately decided to study the planet in even more detail. Boehm mentioned that they recently observed 4 more transits of this planet using Webb in order to understand its atmospheric chemistry more deeply, and that they're very excited to see the results. This entire discovery isn't just about one isolated, distant planet. Its implications reach all the way to our own solar system. Roughly 5 billion years from now, our sun will follow the exact same path, first becoming a red giant, then a white dwarf. Mercury, Venus, and possibly Earth will be destroyed in this process, but the question is, what will happen to Jupiter, Saturn, Uranus, and Neptune? WD 1856b suggests that gas giants may be able to survive, even if their orbits end up reshaped. Ryan McDonald explained this beautifully. He said that we always use telescopes to look into the past, but this is the first time we're getting a glimpse of the future, what might happen to outer planets around the remnant of a sun-like star. It's a bit like a time machine, letting us peer far into the distant future of our own solar system. This is also a rather philosophical thing to think about, that our own solar system will one day meet a similar fate, and WD 1856b shows us that something can survive even after that fate arrives. Jupiter, currently about 484 million miles from the Sun, will certainly be at some risk during the red giant phase. But if it survives that phase, it too might become a survivor like WD 1856b, orbiting forever around its dead star, in a new, closer orbit. Scientists estimate that when the Sun becomes a red giant, its outer layers could expand as far as Mars's orbit, or possibly even further. In this scenario, Jupiter and Saturn would technically remain outside this expanding star, but their orbits would certainly be affected by the process. As the Sun loses mass, its gravity weakens, which could cause the gas giant's orbits to gradually drift outward. This is essentially the opposite scenario from WD 1856b, where the planet migrated inward, but both cases highlight the same underlying truth, that the death of a star fundamentally reshapes the orbits of the planets around it. The same question applies to Uranus and Neptune. Will they also be able to maintain a stable orbit around our Sun once it becomes a white dwarf, or will their orbits be disturbed in some way too? There's no definitive answer yet, but discoveries like WD 1856b are giving scientists new tools and new data points to work on this exact question. This discovery, published in the journal Nature, is the result of hard work by scientists like McDonald, O'Connor, and Boehm, who studied this planet in such detail that they found an answer to a question that once seemed almost impossible. How is this planet even alive? Now it's worth understanding why scientists still call this planet one that shouldn't exist, even though its existence has now been explained. This phrase actually refers to the initial confusion scientists felt when they first spotted this planet. because according to standard models of planetary evolution, no planet should be able to survive a red giant phase in such a close orbit. Until scientists developed the migration theory, this planet genuinely looked like an impossible object. Now that it's been explained, the "shouldn't exist" label is technically outdated, but the phrase still captures just how unexpected and surprising this discovery was when it was first spotted. This pattern has been seen again and again throughout astronomy. A discovery initially seems impossible, or something that shouldn't exist, because it doesn't match our current models. But then, as scientists study it in more detail, they develop a new mechanism or theory that explains it. This doesn't make the discovery any less interesting. It actually means our understanding becomes more complete because of it. WD 1856b is a perfect example of exactly this pattern. Something that once seemed impossible has now become a new kind of example of planetary migration. It's also interesting to think about how the James Webb Space Telescope played such an important role in this discovery. Webb was originally designed to study very distant galaxies, the early universe, and the atmospheres of exoplanets. But its sensitivity is so high that it can detect faint distant signals that no telescope could ever pick up before. A system like WD 1856b, where the planet is extremely faint even compared to its own white dwarf star, requires an advanced instrument like Webb to take such precise measurements, mass, temperature, and atmospheric composition, all in a single observation session. Webb's main advantage is its infrared sensitivity. Most planets, especially gas giants like WD 1856b, emit their own heat in infrared wavelengths, which are invisible to our eyes but perfectly clear to Webb's instruments. In addition, Webb orbits far from Earth, around the Sun-Earth L2 point, where Earth's own heat and light don't interfere with its observations, allowing it to take precise faint measurements that no telescope near Earth could achieve. This discovery matters so much to the astronomy community also because it gives us a completely new perspective on how planets form and survive around white dwarf systems. Scientists previously thought that finding planets around white dwarf stars would be almost impossible, since any close-orbiting planet should have been destroyed during the red giant phase. But discoveries like WD 1856b show that planetary systems can reorganize themselves in new ways even after their star's death. Sometimes through migration, sometimes through the gravitational influence of other stars. Another interesting angle is that the WD 1856 system isn't just a single white dwarf. It actually contains 3 stars total, a white dwarf and 2 companion stars, making the whole system a triple star system. Gravitational interactions in such systems can be extremely complex since each star influences the orbits of other objects with its own gravity. Scientists suspect that the gravity of these companion stars over millions or even billions of years gradually pulled WD 1856b's orbit inward, a process known as orbital migration. This is itself a fascinating mechanism scientists call the Kozai leadoff effect, where the gravity of a second star can stretch a planet's orbit into such an elongated shape that its closest point comes extremely near to its own star. Over time, tidal forces gradually circularize this elongated orbit, but by then the planet remains far closer than its original wide orbit. This exact mechanism hasn't been confirmed in WD 1856b's specific case, but it's a good example of the kind of complex gravitational dance that's possible in multi-star systems, which simply couldn't happen in single-star systems. This kind of orbital migration is actually something that happens in our own solar system too, even if we don't notice it day to day. Jupiter and Saturn themselves migrated during the early history of our solar system before settling into their current positions, a theory known as the NICE model, which explains how the gravitational interactions of gas giants reshape the entire structure of the early solar system. Discoveries like WD 1856b tell us that this migration process isn't limited to young systems. It can happen throughout a star's entire life, even after its death. Another important question this discovery raises: could a planet like WD 1856b ever be habitable? The answer, at least for this specific planet, is no. WD 1856b is a gas giant, meaning it has no solid surface where life could exist. Beyond that, its temperature and radiation environment are far too extreme for any life as we know it. But this discovery does raise a new question for future research. If gas giants can survive around white dwarf stars, could a rocky planet ever survive a similar journey? And if so, what would that planet's environment actually look like? It's also worth mentioning that white dwarf stars, despite their extreme density, lose their light very slowly, meaning they gradually cool down over millions, even billions of years. Because of this, if a planet maintains a stable orbit around a white dwarf, it could theoretically exist in a very long-lasting, consistent, predictable environment, whether or not that environment happens to be suitable for life. This stability is itself interesting to scientists because it gives them a chance to study conditions that will never naturally exist in our own solar system, at least not for several billion years. Some scientists have even proposed that white dwarf stars could have their own habitable zone, a distance at which temperatures could theoretically be suitable for life if a rocky planet existed there. This zone would be very close to the white dwarf, since the star itself is so faint. But if a planet could maintain a stable orbit within that zone, it could enjoy a consistent temperature for billions of years, arguably more predictable than around any normal active star. WD 1856b itself isn't in this zone, since it's far too close and far too hot. But its discovery has pushed this entire concept to be discussed far more seriously within the scientific community. Let's answer a few common questions people often ask. Could WD 1856b ever collide with our solar system? Absolutely not. This system is 80 light-years from Earth, which is quite far on a cosmic scale, and it has no direct effect whatsoever on our solar system. Have scientists resolved all the confusion around this planet? To a large extent, yes, but it's still not entirely clear exactly how the migration process happened, whether the survival theory, surviving from inside the star, or the migration theory, being pulled in by companion stars' gravity, is more likely is still an active area of research. Could other white dwarf stars have similar planets around them? Absolutely, and scientists are actively searching for such systems. WD 1856b is the first confirmed gas giant detected via transit around a white dwarf, but astronomers believe more such systems likely exist. They're just difficult to find because white dwarf stars themselves are so faint. Does this discovery tell us anything about aliens or extraterrestrial life? No. WD 1856b itself is a gas giant where life can't exist, but this discovery does teach us that planetary systems can survive even after their star's death, which indirectly raises new questions about the long-term possibilities for the survival of life as well. So what's the summary of all these discoveries? The James Webb Space Telescope studied a planet called WD 1856b, which orbits so close to its white dwarf star that, according to standard theory, it simply shouldn't be there. Webb measured this planet's mass, recorded its temperature, and detected signatures of molecules like methane in its atmosphere, a historic achievement in its own right. Scientists determined that this planet likely remained safe in a wide orbit until its star transitioned from a red giant to a white dwarf, and only afterward, due to the gravity of other stars, migrated to its current close orbit. This discovery doesn't just tell us about one distant exotic planet. It gives us a glimpse into the very distant future of our own solar system. When our sun eventually reaches the final phase of its life, roughly 5 billion years from now, gas giants like Jupiter and Saturn might survive just like WD 1856b, orbiting forever around their dead star in a new reshaped orbit. Perhaps the most beautiful part of this entire discovery is that it reminds us that an ending doesn't always mean the end. The death of a star, which at first glance seems like complete destruction for its entire planetary system, can actually be the beginning of a new chapter for some things within it. WD 1856b, orbiting endlessly around its dead star, is living proof that destruction and survival can both be part of the very same cosmic event. If you enjoyed this video, please hit like, subscribe to the channel, and let us know in the comments. Do you think gas giants in our own solar system, like Jupiter and Saturn, will survive once our sun becomes a white dwarf? See you in the next video with another amazing space discovery.